Okay, thank you for the introduction, and thanks to everyone who came for the talk right now. And I guess there is no secret at all that the release of GPT-4 from OpenAI and any other advanced models have significantly revolutionized our industry and the way we use different tools in our modern lives. And I assume that many of you use different LLM for different purposes on everyday basis. But looks like that the progress in the recent times starts to slow down and caused active discussion in the professional community whether we are going in the right direction towards AGI or we do not, and we have to somehow alter the way we are going. And one of the most heatedly debated topic in the industry is the reasoning abilities of LLM, whether they are behave like human cognitive abilities, or they do some sort of sophisticated memorization or pattern-based thinking, mimicking the real reasoning abilities. So I hope that now is a perfect time to stop and talk about how does reasoning actually work in language models and what do we know about it, and answer three questions. So the first one, what is reasoning and why it's important for language models? Quite basic and formal questions among three. The next one is, what do we actually know about LLM abilities to reason? And the last one, how does it affect our decisions when we try to build LLM-based applications? And let's jump towards a formal definition for the reasoning. And it could be seen, the reasoning is the process of drawing conclusions based on available information. That usually consists of a set of premises that could be formed into logical chains and so on. But this definition sounds quite simple to understand, but hard to measure, and it's really hard to measure the degree of reasoning abilities in LLMs. So researchers mostly dedicated their studies to manual assessment and so-called proposed reasoning tasks that could be divided into a few categories like logical reasoning tasks, common sense, mathematical, their combinations, and so on. And for today's talk, I would like to stop and talk about logical abilities to reason in language models. So for that, we have to discuss three types of logical reasoning approaches that we use as humans. The first one is the deductive reasoning. That's an approach that allows us to draw conclusions from general rules. For example, if I burn my finger, if I put my finger in a fire, it will burn. So this 100% certain conclusion without any doubt, and that type of reasoning we use on everyday basis for numerous decisions we're making. The second one is inductive reasoning pattern that uses historical data, patterns, associations in order to come from specific observations to general conclusions. And as an example of it, we can say that if people talk about this restaurant that they serve the bad food, then probably it's bad and it's not worth to go there. And that sort of conclusions, they are not 100% sure, but they are quite certain. And the last one is the abductive reasoning. It's the creative reasoning pattern where we have a limited observation, and we try to make different assumptions in order to come for the best prediction. So with this type of reasoning, we usually conclude different hypotheses, we test them, and come to specific observations that we can say, okay, probably that's true. So done with the formalities, why LLM reasoning in LLM matters for us as developers or people who make business decisions. So reasoning matters in order to understand where LLMs excel and where they fail, in order to recognize what's their limits when we build applications that uses LLMs under the hood. And the last one, how well does with what degree of, how sure could we be to deploy these models and allow them to perform without control on out-of-distribution tasks? Let's jump to research dedicated to deductive reasoning. So LLMs show some capability to follow deductive logic, but they're prone to shortcut pattern matching, and essentially it looks like that LLMs tend to rely more on pattern matching and memorization from their training data rather than logical assumptions. Second one is the compounding errors when models try to do multi-step reasoning, and this means that LLMs tend to make errors early in the chain of premises that lead to like combinatorial effect in the whole error. Third one is their sensitivity to premises order, and by that research shows that when we try even a little to reorder premises in our reasoning behavior, even if these premises are logically equivalent, LLMs usually tend to confuse a lot. And the last one, that LLMs struggle with logical operations, and in particular with the complex one like negation or complex structures like De Morgan laws and so on. Let's consider a few practical examples. So that's the picture from research conducted by researchers in MIT and Boston University, where they tried to find out whether LLMs tend to rely on transferable reasoning skills, or they rely mostly on memorization and pattern matching. For that, they've took different tasks that they've called and use their default versions. For example, arithmetic tasks where we have to add or multiply two numbers in the base of 10, and provided their counterfactual versions where, for example, model have to generalize and do the same task, for example, in a base of 9 or 16. If you know the base principle, it's not a big problem. The other tasks include code execution and code generation, where, for example, they instructed LLMs to interpret and generate code under the fictional language called ThonPy that only differs from Python by using one-based indexing instead of zero indexing. But the thing is that's quite a normal assumption, because there are some languages that use one-based indexing like MATLAB and R, so it's not something super imaginable, and this assumption, you can come to this assumption when you try to solve the problems on your own. And what they found out that even under the scenarios using zero-shot chain of thought methodology that simply put instructs model to follow and think step by step, the the performance is significantly better on default tasks rather than counterfactual tasks. The next paper was published by Apple, and it made a lot of noise in the community. As I remember, it was discussed a lot on the internet. So what they've done, there's a data set used for LLMs benchmarking called grade school math that consists of tasks that usually require up to 8 operations, basic mathematical operations like addition, multiplications, and so on, to come to the final answer. And what they've done, they wanted to test quite the same thing that the authors of the previous paper would like to. And for that, they took examples from this data set and created so-called templates, selected 100 examples, identified where names in these examples, different numbers, and so on, crafted a template that they later used to generate more examples with varying numbers, entities, and so on, and measure what's the performance of the model will be on this modified version of the data set. And as seen from the graph on the right, the performance of the most advanced models like GPT, Mistral, and Google's Gamma haven't dropped significantly, but in other cases it's started to drop even at this moment. So they decided to go further and created the second version called GSM No OP. And the thing with this data set was that they took the examples and introduced a condition that was absolutely not necessary but not confusing to the task itself. In this example, we can see that the task is about how many kivas Oliver will have after some sort of simple math, but with a small addition that 5 of these apples were a bit smaller than average kiwis, sorry. And it looks like that, and they can come to the conclusion that after benchmarking different models, on such tasks where you add some simple but not necessarily conclusion, the models, even of the most advanced models, significantly drops from 17 up to 65%. And I guess that's it with the examples for deductive reasoning, and I would like to move to inductive reasoning. LLMs can infer general rules from specific examples, but with the following limitations. The first one is inconsistent rules, and that is when LLM infer rules, usually they often diverge from those a human could do. Secondly, the generated hypotheses were too long and inconsistent, and sometimes context irrelevant to the task they were given, and they also sensitive to task framing, and by that, researchers mean that when you alter the task description, LLM's performance and reasoning behavior could significantly shift in unexpected ways. One of the examples of works dedicated to inductive reasoning is the one where authors provided a framework for hypothesis generation, and they've done it in the following manner. So at first, they generated hypotheses for different benchmarks they have chosen in order to solve the task. Then they've selected one of these hypotheses or any of them and start to validate it. So basically they try to pursue the manner of how people think about it. And they've come to the results that says that LLMs tend to, they are great at generating a lot of different hypotheses, but they are really, really bad at applying them to the task for which they have generated the hypothesis. And the last one is the abductive reasoning, where LLMs tend to be weaker in generating different hypotheses, and they are limited in their creativity, variety. They usually hallucinate and provide some details that are not in context with the task. And they also tend to be weaker in providing hypotheses that have to include multi-step reasoning, and the coherence of this multi-step reasoning is a big problem in such scenario. While I talked a lot about the works dedicated to reasoning, there's one important factor and how we evaluate the performance of reasoning behavior in language models. And it could be done in different ways. Sorry, I got a little bit wrong with this particular bullet point, but evaluation could be conclusion-based when we look at the output of the reasoning result of the model. Then the evaluation could analyze reasoning steps for coherence and logic. That's actually how many cognitive sciences do. And they also could evaluate interactiveness of the reasoning and not to look only at the conclusion and the rationality chain. You can dynamically alter different tasks and look how with these alterations your model behaves in what reasoning steps it produces. And the last one, the most difficult one, is when you try to examine internal workings like attention layers or other blocks of the model in order to find out what affects reasoning capabilities and what not. But the problem with the reasoning evaluation that unfortunately there exists a problem called data contamination, and it's directly connected with the memorization of information by language models. So there is quite a good resource you can find online that called LLM Contamination Index, which is essentially a table that shows the different how exposed different corpora was for different models, at what percentage, what subset of this benchmark was leaked. And that's a problem you have to keep in mind, because if there's a significant chance that model could remember the examples from the benchmark, your assumptions about reasoning abilities of that model and about its behavior could be put under question. And that is a significant challenge for reasoning evaluation. The other interesting thing that I found out recently by the study conducted from Princeton University, that LLMs reasoning greatly influenced and sensitive to input sequence and output sequences probability. And by that, authors conducted the following thing. They've chosen high probability outputs and inputs that was presented in the training corpora of the model, the sequences that rarely appeared in the corpora and with the low probability. And they decided to test because language models usually trained on a task called next word prediction, and you have to model the probability of the next word. There is a hypothesis that the reasoning abilities in the process could be significantly affected by the training procedure the generative models used. And they found out that the reasoning and task accuracy greatly depends on how probable is the output of the models, and they've done it by using two tasks, like reversing the given sequence. So if you have Alice done something, you have to reverse something done Alice, and so on. And they found out that with the high probability inputs, the output is also high probable. Okay. And the last thing is about the increasing the performance of language models in reasoning tasks. And it's the technique called chain of thought that proved that it worked, and it does significantly change results in a better position. So the thing about chain of thought is that you tell the model, let's think step by step, and by that you force the model to start process the intermediate steps that it uses to come to the conclusion. Or there's a second way when you can decompose the problem, like on the screen, where you give an example, a detailed one with the step, we do this, this, this. And this simple approach already can boost the reasoning performance and the accuracy on the given data sets. So coming to the conclusions, what we can get from the available information about reasoning abilities, that mostly LLMs tend to rely on pattern matching than logical inference and reasoning. And by that, and using this, we can try to we can deploy such applications for scenarios where we have to rely on factual reasoning with cautious, because these models may be prone to inaccuracies. The second one is biases, and by that biases I mean cognitive ones, when models like favoring believable but incorrect conclusions. And in order to leverage that, we have to carefully monitor applications to prevent bias or misleading outputs, especially for industries like HR tech, customer support, and so on. And also models, finally, struggle with complex reasoning that requires multi-step compositional generalization or contextual dependencies. And the idea we can use for building the applications that we have to use LLMs with caution for scenarios requiring deep reasoning, and try to carefully look at what we're actually trying to build. So I guess that's it, and I would like to answer the questions if you have one.
Let's see if we have some questions. Yes, we have it here in the second row, please.
Yeah, thank you for... Hello. Yeah.
We can hear you.
Thank you for this really interesting presentation, very interesting topic. And what bothers me a bit is to make peace in my mind with the two ideas. One is, okay, LLMs are simply trying to predict what the next token will be. Mm-hmm. And then suddenly you have this whole thing about the reasoning. right? So how do you make peace in your head with that? Like where the reasoning actually appears from, it kind of emerges out of something. So how can we be sure that we are not just fooling ourselves, that it simply looks as if we have some reasoning there? Or are we talking about reasoning simply as a placate word to describe this kind of analysis that you're describing here? Yeah.
No, actually, the question you asked is the question that commonly appears on the debate about whether LLMs have human-like reasoning abilities, so they can make conclusions, decisions that tend to be more like what human does in everyday life. And answering the other part, though large language models do simply learn next word prediction as the main task, there are two important factors that allow for reasoning abilities to emerge in such models. The first one is the amount of data we use for their training and the size of these models. For example, GPT, Llama, and other super big models that have more than 400 billion parameters require big infrastructure, and they will probably fed the whole internet in them. And somehow we still don't know how these reasoning-like abilities tend to exist in such models. So that's important, but understanding whether they're truly reasoning or not is over-complexified by the inner workings of neural networks. So, because essentially neural networks is a black box and we can easily interpret it. So that's why there are many studies that make assumptions, test them, and come to the conclusion, okay, probably that looks like that. So I guess that's it.
Yeah, thank you.
Thank you. Another question? Well, it seems we don't have any more questions. Thank you very much.
Thank you everyone for listening.
This is for you from the organizers. Thank you once again.